Okay, welcome to Physics 130 review. We are going to do problem 11 on the review problems, and that is an Atwood machine, so a modified Atwood machine. We have one mass sitting on a table. This is M1. It's connected with a rope and pulley to a hanging mass, M2. And the problem says the hanging mass is 2 kilograms, so M2 is 2 kilograms. Here's our givens. And then the mass on the table is 5 kilograms. And there is friction. It comes up later. So the first part, part A, is just to draw a free body diagram of M1 and M2. So M1 is the mass on the table. So we do our free body diagram. We have M2G, and we have the normal, and we have tension, the rope pulling it that way, and we have the force of friction. Let me make it a little bigger. Okay, and then we have M2, the hanging mass. It has its weight, M2G, oops, sorry, this is M1G, and then we have the tension going back. Okay, these tensions are the same. Okay, and then we need to set up a coordinate axis, so whenever we do these problems with linked masses, we want to think about how the system is going to move, right? So this mass will accelerate downward, this mass is going to accelerate to the right. And so I want to define that direction as positive for both of my masses. So meaning that I want to use my plus y direction down for the hanging mass, and my plus x direction will be this way for the mass on the table, and y could be that way. Okay? And so whatever acceleration, since these are linked, whatever acceleration this one has is going to be the same that that one has as well. Okay, so that's part A. Part B says apply Newton's second law to M1 and M2 without plugging in any numbers. Find acceleration. Okay, so let's start with the mass on the table. We can sum the forces in the x direction, gives us MAX, and we can sum the forces in the y direction, that's MAY. The mass is not accelerating in the y direction, so that's 0. Okay, so I want to look at my free body diagram when I'm summing the forces. So I said this is my positive x direction, so I have tension is positive, I have the force of friction is negative, and that's going to produce an acceleration in the x direction. And in the y direction, I have a normal minus m1g equals 0. So the y equation tells me my normal is m1g, which is typically the case if it's not accelerating and it's on a flat surface. Okay, so I can go down here and replace this with mu times the normal equals, so this is all m1, m1a, and my normal comes in from the y equation, so I can get t minus mu times m1g equals m1a. Okay, so I don't know my acceleration and I don't know my tension, so now I'm going to use the equation for m2 to help provide another constraint. So I'm going to sum the forces in the y direction, and that will tell me what the acceleration is for M2AY. Again, I said down is going to be positive, so when I sum the forces on M2, gravity is positive, tension is negative. So M2G minus the tension equals M2A. And this acceleration, like I said, the masses are linked, so this acceleration in the y direction is the same as that acceleration in the x direction. And here's my tension again. So I have two equations and two unknowns here. Right, that one and that one. Okay, so if I want to get rid of one of the unknowns, I could solve this, for example, for tension and plug it in over there. So let's do that. So tension equals M1A plus mu M1G. And we're going to plug that into this equation, and we'll write that again down here. So we get M2G minus M1A plus mu M1G equals M2A. And now A is my unknown, so I got to move that over to the same side. So I'm just going to bring this to the center here. So we get m2g minus m1a minus mu m1g equals m2a. I'll add my m1a to both sides. Okay, so I get m2g minus mu m1g equals m1a plus m2a. And if I factor out my acceleration, I get m1 plus m2a. And now I want to divide both sides by m1 plus m2. So I get that my acceleration is m2g minus mu m1g, so the weight of the hanging mass minus the force of friction, divided by the total mass, so my system mass. Okay, so that's what I get for my acceleration. Alright, so then C basically is just asking me to plug in, so it says given that the coefficient of friction, mu, equals 0.15, find the acceleration. Okay, so now I just need to plug in. So my acceleration is m2, which is 2 kilograms times the acceleration of gravity, 9.8 meters per second squared, minus my coefficient of friction, so 0.15, times m1, which is 5 kilograms, times the acceleration of gravity, 9.8 meters per second squared, and then I divide by my total system mass, which will be 2 kilograms plus 5 kilograms, otherwise known as 7 kilograms. Okay, so if I plug that in, I should get that my acceleration is 1.75 meters per second squared. Okay, and then the last part, D, says if the 2 kilogram mass is initially 1 meter above the ground, so here's my m2, it's initially 1 meter above the ground. When will it hit the ground? So the system's going to start moving. How long does it take to travel that distance? So this is a kinematics problem. Okay. So we can set up our coordinate system a little bit different. So I know what the acceleration is now, right? I know that the mass is going to be accelerating downward at a rate of 1.75 meters per second squared. So lots of different ways that we could do this. I'm going to just say that I'm going to use the equation y final equals y initial plus v initial yt plus 1/2 ayt squared. And for this part, the kinematics, I'm just going to use my more traditional plus y is up, which just tells me that my acceleration I need to just plug in as negative. Okay, so y final is 0, y initial we know, it's starting at rest, so that goes away, and then we have ay t squared. So if we want to solve for t, we have negative 1/2 ay t squared equals y initial. And then we can get t squared by itself is y initial divided by negative 1/2 ay, and then we take the square root. Sorry, my dog wants to come in and learn physics. Okay, so we get the time is the square root of y initial over, so let's make this 2, negative 2y initial over ay. And then we can plug in, so negative 2 times 1 meter divided by 1.75 meters per second squared, remembering that the way I set up my coordinate axis here, acceleration is negative. So if we plug in our values and solve for time, we get t equals 1.07 seconds. Okay, a little tricky that I just flipped the coordinate system here, but it really is a separate problem once I know what the magnitude of acceleration is and the direction. And that's the end of that problem.